Supreet, I am making you host.
Not it.
Yeah, I'm making. Okay, yeah. Okay, done. Durgesh has to be made a co-host. Tanaka.
Hi, good morning.
Good morning.
Good morning, Prof. Tanaka.
Hi, good morning.
Supreet, Durgesh is chairing this session. So, yeah, made him. Okay. So, this session.
Hello.
Hello, good morning.
Good morning. You can hear my voice, right?
Yes.
Yeah, I just wanted to test before my turn comes. Shall I just test the screen as well, whether sharing and
Yeah,
all?
you can try. You can try sharing.
Yeah, just to. So, do I have the co-hosting right to share the screen?
Yeah, Supreet will enable that.
Okay. Yeah, I think I have. Do you see my screen?
Yeah, but
Yeah,
not
yeah.
in.
Can see, right? Okay.
Yeah, but not in presentation.
Yeah. Now should be okay, right?
Yeah.
All right. So then that's fine. So let me just unshare it.
If Prof. Young is already here, we can start. Okay, Durgesh, maybe start.
Good morning, everyone. Welcome to the session I of BICPAMA 2021 conference. My name is Durgesh, and I will be chairing this session. This session is called Spin-Based Neuromorphic Computing, Spin Orbitronics, Skyrmions. The session has 3 invited talks, and each talk will be of 30 minutes, followed by 10 minutes of discussion. The first talk will be by Professor Yang Hunsu from National University of Singapore. The title of the talk is Artificial Synapses and Neurons Using Spin Orbit Torque Devices. Prof. Yang, please go ahead.
Oh, can you hear me?
Yeah.
Okay, very good. Thank you very much, Chairman. My name is Hyunsu Yang from NUS. So today I'm going to talk about artificial synapse and neurons using spin orbit torque devices. So if you look at the conventional, von Neumann architecture, we have input device, and then we have a control and memory and output device. So basically, our processing and the storage units are separated, and the responses processed in a sequential order. So because these regions, we have low efficiency in data processing. On the other hand, if you look at our human brain, probably you've heard this many times in this week, is highly connected and parallel. And it's like, you can learn and then you can train those. And also it enables a very low power and fast processing. So the neuromorphic engineering is developed to mimic basically this brain-like computing and perform low precision tasks like face recognition. So if you look at now some more details, how our brain process this information, basically there are 2 main objects. One is neuron, and that is another one is a synapse. So synapse basically gives weight to the input signal and modulate the membrane potential of the another next neuron. And when there is an input signal from synapse into neuron, basically the potential of the neuron increase until it reach threshold. Then the neuron will fire the signal to basically next synapse. Once it fire, basically the potential will decrease, reset to base value. So that is all done by sort of automatic function, and it's not very easy to implement in hardware using our solid state devices. So we require devices to emulate these synapse and neuron all together, and to mimic our brain functionalities in an energy efficient way. So now let's look at how many neurons and how many synapses do we need to make to mimic our brain. If you look at our human brain density of neuron, we have about 1 million neuron per square centimeter. And then we have 10 to 10 synapses per square centimeter. And the power consumption is about 2 milliwatt per square centimeter. And total power consumption is about 20 watts. So now if you look at, how many connections do we have per 1 neuron? So if you divide by this number of synapses by the number of neurons, and you can find out we have about 10,000 connections simply, per each neuron. It's an amazing number, if you think about any device has 10,000 connections from a single device. Can you imagine? Is this possible? I think it's very difficult to implement using our current generation nanotechnology. Well, the other question would be, can we make, for example, 1 million neurons per square centimeter using our current fabrication technology can we implement 1 million neurons per square centimeter? If you look at the current CPU, 1 cm by 1 cm, area, we have 10 billion transistors. So this is certainly possible. But I want to point out, this amazing connectivity is very difficult to mimic using current technology. But nonetheless, we should start something, by research. So our, motivation is, if you look at this, processing is done by basically ionic migration. This potassium, these ions move in and out membrane basically, and then propagate along the signal line, basically inside our human body, and then it change the potential and then fire and go back to the initial state and so on. So basically the human body is processed, signal processing is done by ionic, signal processing. It's not by electron. So we thought we should mimic, as much as possible. So our history begins, from the oxygen engineering in the spin-orbit Toc devices. So initially in 2015, we found, depending on the number of oxidation in our device, we can change spin-orbit Toc sign. For example, in a very conventional platinum copper ion boron, bilayer, then we typically kept with the very thin MgO and the silicon oxide on top. And depending on the silicon oxide thickness, once we kept, silicon oxide like more than 2 nanometer, for example, then we find typically positive, spinor angle coming from platinum, as well known. That is shown in this switching sequence here. Maybe let me use laser pointer. But on the other hand, once we kept the silicon oxide less than 1.5 nanometer, we find the switching sequence is opposite, as you can see in these, yellow boxes. This indicates basically effective spinor angle is negative here. So depending on the capping thickness of silicon oxide, you can see, the effective longitudinal spin orbit field, becomes negative. So this is very strange. It's impossible, to understand by spinor physics, and this suggests some role of interface. So at that time, we interpreted, this should be understood by also the contribution of the interfacial Lashba effect due to oxidation. So then later on, we continue this, approach, and then we put a gate on top of the device. And then also we put the gadolinium oxide, because gadolinium oxide is known as oxygen reservoir. So it can contain lots of oxygen. Depending on the gate voltage, you can push those oxygen from gate oxide, gadolinium oxide, for example, into the cobalt layer, for example. And if you apply positive, voltage, you can suck those, oxygen from cobalt back into the gadolinium oxide. So we can apply, from initial state minus negative 4 volts, then we will push away this oxygen into cobalt. So then we can, have effectively negative spinor angle. Then if we apply positive gate bias, and then we can bring back to, a positive spinor angle like behavior. So we can basically switch back and forth. That indicate we can, encode any information we want depending on gate oxide. So even we apply same current in the channel, and then let's assume there are many bits on top, depending on the gate, voltage, we can, encode information 1 or 0, whatsoever we want, by just changing the, gate voltage. So this will be quite useful to make some kind of spin logic device. But also we find very interesting behavior depending on the, the sort of programming time in this device. So we apply negative voltage, then eventually this should go to, effectively negative spinor angle because of oxygen accumulation in cobalt layer. But depending on how much we apply. So we apply 30 second, 50 second, additional 40 second and so on. And, applying very, very slowly in a way, we found there is a gradual, change of this status, of this device. And then from effectively negative point, now we can apply positive voltage, and then you can see, it will bring back to the positive state in a very gradual fashion. So this indicates basically, we can think about some kind of analog-like application, which is, neuromorphic devices. So if you look at this oxygen migration-based, our spintronic synapse, and compared to the previous two-terminal, memristor-based synaptic device, also they use some kind of, ionic migration, and typically that is oxygen. Because of two-terminal, they can have very high density, and also, relatively simple to fabricate. But they have also read and write latency, and then also the read error rate is very high. And importantly, they do not have any, negative synaptic weight. Basically, you can only, keep connecting more and more. You can increase their connectivity by injecting more oxygen. There is no way you can, subtract this oxygen. So what they are doing is keep accumulating enough, oxygen and make a so-called filament formation. Then you break those filaments to reset. On the other hand, in our case, you can bring back at any time. For example, at this particular point, you want to bring back to the positive, you just switch the gate voltage, it will bring back to the positive state. So basically, we can, apply any negative, even positive, synaptic, weight. That is the main, advantage of this, spintronic synapse, what we showed using oxygen migration. So we show, many, basically, biologically similar functions, such as, potentiation. You increase potential, and as I show, we can, depress. Even we can implement the negative, increasement of this potential, and also depression in the negative, weight. We can also change the amplitude of the excitation, voltage. Then we can slowly increase with low voltage, 8 volt. But if we increase to 10 or 14, you can see the potential will increase, quickly here. We can also change, the pulse delay. If we keep applying the pulse in a very frequent way, that is the red one, 10 millisecond, we can increase the potential quickly. But if we apply the potential, kind of, once in a while, then you can see the potential will increase very slowly. One of the very important data we need to show whether this is like a really synaptic is the spike, basically time dependent plasticity, STDP. So we use basically 2 pulses, and depending on their relationship, whether they are really close to each other or far away, if they are very close to each other, basically the influence of the previous pulse to the next one should be large enough. So that's why we have a very large change of the delta R, which is our potential. If those 2 pulses are far away in this data point, for example, there shouldn't be any relationship, because the previous one cannot affect the next one. So that's why the delta R is almost 0. So this is so-called STDP, curve. So as you can see, our device mimics, many, real synaptic functions. We can also show learning and forgetting. We can, program it with the applying certain positive voltage, for example. Then we just remove our input. Then what will happen? The signal can decay gradually, over time. And then we measure those relaxation time constant, and then we plot those as a function of the training pulses. So depending on how many pulses we initially train, then let it relax, we find the time constant can change, from 200 seconds to, about 1,000 seconds. So we can easily manipulate, those decaying, forgetting time. So this is similar, if you study, more frequently, basically you can have a long, term relaxation. That is basically long-term memory, our human brain. So if you study, less, basically information will go away, quickly. So that is kind of, short-term memory. So we show, this spin-orbit talk-based oxygen migration can mimic, many functionalities of our, synapse. Then I want to move to now neuron, whether we can make a neuron. Compared to synapse, the experimental demonstration of spintronic neuron is very limited. One of the major problems is spin-based neuron are either non-spiking or they require a reset pulse. So if there is input signal, basically the potential will increase until it reaches this threshold. Okay, then once it reaches this threshold, it will fire. After firing, the potential should decrease to this baseline. Right? This cannot be done automatically in a typical, spintronic devices. We have to give additional reset pulses. So that is basically a problem we want to address. So our approach is to utilize exchange bias using ferromagnet and anti-ferromagnetic material. So if you have exchange bias, basically you can shift in the MH curve into one direction. Then if you measure the spin orbit torque signal in those devices having a heavy metal underneath, and you apply current here, basically you can switch this cover into certain direction. Then what will happen? Because of exchange bias, this magnetic moment or spin direction can come back to the initial direction. So once you go back to the zero excitation current, basically it will move back to the initial state. So that is our main motivation. So experimentally, we show having such exchange bias, the SOT, you can basically increase your current in heavy metal and you can fire. That means you switch your magnetization into a certain direction. Then once you bring back your current to almost zero, then you can see the signal will follow the first trajectory, the switching trajectory, and then go back to the initial state. And that is also tunable depending on the in-plane assisted magnetic field, because right now we are dealing with basically very simple heavy metal. So we need the external small magnetic field for assisted deterministic switching. We can also show at zero field. In this case, there is no deterministic switching, so we can fire in any direction. We can apply negative current and positive current, and we can fire and then go back to zero current, and then that will also bring us the initial magnetization direction. So basically, we already demonstrated this device doesn't require any reset pulse. And then we also scale the device size and see what happened. This red one is 20 micrometer width of the channel. And then we reduce to 10, that is this green color. And then 400 is this blue color and so on. So you can see once we make a smaller device, basically the required current is getting smaller. So that is correct scaling. And also we maintain this automatic reset function, even in a very small device. Also, we test stability of device. So after trying 500 times of switching back and forth, then we measure, same response. And then once we increase the current, it can fire and then it will go back to the initial state. So even after 500 round, device, still has a good stability, and there is no change in terms of, its functionality. So also we try to now then mimic the stochastic behavior, because this is another very important feature of real biological device. So we achieved this stochastic neural-like behavior in smaller devices. So once we make more nanoscale devices, we found that there is a higher chance to achieve this stochastic behavior, which is expected. And then if you look at this switching, part here with the higher current, you can see the data is not very smooth. And once we magnify those parts, you can see lots of fluctuation happen. And that also depending on the injected current level. So if we apply, for example, 3.35, you can see the black, line here, black data points. Basically, no change because the current level is not enough, to switch. Now we give, more pulses. This is basically the pulse-based switching. So we give more pulses at a certain amplitude. You can see, blue one, 4.4, 04 milliamp, pulses. You can see blue ones fluctuate here to here, and then even we have many, many intermediate values. If you apply 4.1 milliamps, that is the yellow one, you can see it's already fully switched. So, and it maintains the saturated, value. So now we can plot those switching percentage or switching probability as a function of the input current. And then we can see this nice sigmoid-like, function. Once we have a sigmoid-like function, then it's very useful to apply in many neuromorphic engineering applications. So we try to now apply this one to voice separation. Voice separation is very easy for human. You go to, any party or your friends are talking, you can easily tell who is talking. And then even you can listen one particular person's voice if you, just, pay some attention to those. So this is the amazing feature of human brain. And that is the result of neuromorphic, sort of engineering. But if you ask a computer, for example, to take it out the particular person's voice and then, implement what is this person talking about, then it will be really, really difficult problem. So that is basically the cocktail party problem. And interestingly, each person has, very particular, timbre. And there is a pattern, and if you do basically the Fourier analysis, there is a sequence of the harmonic waves, composing certain voice. For example, if you look at a singer, you can see many repeating harmonics. So that's why the sounds, it sounds like really beautiful, basically. But if you look at the normal person, this is basically the frequency spectrum. Still, we have this higher harmonics, but not as much as a singer. What is the challenge in the voice separation problem? It's very difficult to a machine, especially very challenging in a noise and far field condition. That's why if you look at the CCD camera and so on, basically they all relying on image. Let it alone the basically the security and also personal issue. So what are the applications? We can apply for speech recognition and simultaneous interpretation, chatting robot, security monitoring, self-driving car, and etc. I think there will be a huge applications in the future. We have to identify, for computer, how many speakers, for example, n number. Then it's a kind of a permutation problem. The order of speaker has an impact of during training. And in reality, we don't know what is the real sequence. So that's why it requires tremendous training data set. Very complex the training cycle, huge power consumption. So far, the best algorithm, the word error rate is about 23%. It's very high. That's why still we can't really utilize this voice recognition in our cell phone. As you can experience, if you try to use your voice to give some word or command, in a very noisy environment, it mostly fades. So what our approach is, we want to eventually we want to make a real-time audio signal separation system, which can separate the audio signal of a target source from multiple signals. So we want to use this stochastic neural device, which we showed earlier, and which can mimic the firing behavior of neuron, but at the same time is stochastic. Basically, we can tune those firing frequency depending on our input current. So how we can do those? Basically, we need to use a group of these stochastic neural devices to mimic the behavior of population of neurons. So in reality, if you look at our human brain, it's not just by a single device. It's a group of devices, and then each one gives a small input, and then those signals will be merged into a neuron, and then those will affect also your neighborhood neurons. So it's basically a group processing. And this nonlinear population behavior can be constructed from the weighted sum of those tuning curves of the population of neurons. So basically, we need to allocate each neuron into a specific frequency, and then we're gonna add up those, and then we will eventually adjust the weightage of each neuron device. So we want to have this initially, for example, 15 cells. So each cell basically represent the spin orbital device, which can change its weightage, and then those are connected with FPGA, and then the weight stored in a separate memory. And then, as I mentioned, each device will have basically some stochastic neural device. It can be, the SOT devices I showed you earlier. So how do we train those, devices? So we learn the weight of different target source. For example, once we use 15 SOT as a basis, then basically this should represent some kind of a sound filter. So we need to tune each junction to a different range of input current by applying individual current to the bias, the contact point of each junction. So we're gonna modulate basically this response curve, okay, into like this kind of sound filter, right? Then we also need the inferring process. Basically, we use this sound filter to separate a target sound. Okay, so we use weightage memory to store the weight values, and we use also FPGA to control the data transfer between this memory and our computing cell. Okay. So we want to show you this preliminary result. Right, so let me click. I need to change to normal cursor. So you can see this is a mixed, sound of violin and piano, right? So and you can hear this is only, separated violin sound. Of course, at this moment, this is done by our, simulation software. Okay, so we first train. What we did is the system using, various data set of violin sounds. Then we input the frequency spectrum of mixed signal, and then we obtain the separated violin, sound. Then we finally apply inverse Fourier transform to obtain the separated signal. Okay. So what is the advantage of this spin-based neural-like computing system? Obviously, as you know, the spin device is very, very high endurance. In a memory, you can easily switch like 10 to 15, cycle compared to flash memory nowadays, below 100,000 cycle. Ultra low power is a typical advantage of, spin device, compared to some other, very high power consuming charge device. Eventually, this spin device will allow us to manipulate in a nanoscale speed. That is certainly possible. And also because we are using, group of these devices, eventually it will be noise and fault, tolerant. So even though in one device, failed, it doesn't work. But, eventually if you look at the output will be more or less similar, because we are relying on so many, devices. So, couple device failure wouldn't affect our results. Okay. So that's why, this population output corresponding to this time average of the stochastic, pattern, basically that makes the robust to noise, and even the imperfection of a single junction can be neglected in a population coding. So I show you basically, starting from how to make a, spintronic synapse. Then we move to spintronic neuron, and then we try to solve, automatic firing function in a spintronic neuron. So in our device, we do not need any, reset pulse, basically. Then based on this neuron, what we found is once we scale down to, nanoscale, for example, hundreds of nanometer channel, then we find the switching behavior is stochastic. So once we have a stochastic behavior, then we find, the function of this stochastic switching probability is like a sigmoid function as a function of input current. Then using this sigmoid function, then we now realize, we want to realize eventually this voice separation system, but we already show by, simulation, this sigmoid-like function will enable us, to separate those, multiple signals, and then we can target only one, for example, voice eventually. Right. So for this, I want to thank, a few of my key group members, Dr. Chiang, who did this stochastic investigation, Dr. Jia Su, who did this basically the whole system implementation using FPGA and memory and so on. And Dr. Rahul Mishra, who is now a professor in IIT Delhi, who did earlier work of the Ionic-based, Spintronic synapse. Thank you very much for your attention.
Thank you, Prof. Yang, for excellent talk. The talk is open for discussion now.
Hinsu, very interesting talk. Thank you. So all your demonstrations, are they based on the AHE voltage?
That's right. Yeah. Right now we are relying on the AHE. Yes.
So if you compare the RXX versus RXY, which one is usually larger in your sample?
I guess it will be similar, because they typically make kind of a really cross-shaped device.
Mm-hmm. Mm-hmm. Okay, thank you.
Yeah. Please raise your hand and ask questions. Yeah, Dr. Ramu, please go ahead.
Yeah, thanks, Prof. It was a nice talk. So I have a question regarding the power consumption for the synapse devices. In the first, in the few of your first slides have shown me like there is need to be voltage gated that is applied in order to switch the spin Hall angle.
Sure.
Because I'm actually speaking in with respect to the endurance of the device, that we need to apply some voltage there to see. So what is the endurance of the device with respect to the voltages that we're applying there?
Okay, so right now we are applying relatively large voltage, obviously compared to the the CMOS processing. Our applied voltage is much larger. For example, you can see this device. We are applying plus minus 5 volts. Right now, CMOS is even below 1 volt. This is highly depends on the thickness of the gate oxide. Okay, so we are using actually very, very thick gate oxide right now. Don't have a number here, but basically, not only 3 nanometer, but on top we put another tens of nanometer gadolinium oxide on top of this. So basically, if you adjust the thickness of this oxide, and you can increase the electric field, then you can reduce the voltage. So this is an engineering issue, and then recently there was a good advance by Jeffrey Beach Group in MIT, and then they were able to use much lower voltage by reducing the thickness of this gadolinium oxide. So I think it's a device scaling issue, and right now we are using quite giant whole device. Typically tens of micrometer in terms of width. That's why everything is too big. But eventually, if we can make a nanoscale, then we can also narrow down the thickness of this gate oxide. Then your electric field will increase. Then subsequently, you can only use a small gate voltage. So that is possible.
But following this, I have a question, because as you are telling, like you want to reduce the thickness further into the thinner, right? So in that case, there will be chances that the breakdown of the gate may happen, right?
Sure, yeah, that is always possible. So that is another issue of the reliability of the modern flash memory, because they are making so small and very thin. That's why if you repeat them, for example, nowadays even I think 50,000 cycle, of writing. So basically this electron will jump into your floating gate direction through this oxide. So basically you keep damaging your oxide. That's why there is an issue of this cycling. So similar issue will happen if you use. But in our case, interesting thing is we are not using very large current penetration into this oxide. Later, what we are doing is just apply the voltage on top. Then just we are sending ions, oxygen ions. We are not really penetrating this high potential the electrons into this oxide. So my speculation is our device stability will be probably much better than flash memory.
Thank you.
I think we have time for one more question, maybe.
Can I ask one question?
Yeah, sure.
Yeah, thank you, Prof. So I want to ask your demo, the synapse behavior. Also depend your use crossbar device. They also depending on the domain wall position or domain wall motion.
Oh yeah, this is a very good question. Yeah, obviously, if you look at the detailed switching mechanism, everything is based on domainal motion, unless you can make a single domain device. But if you want to make a single domain device, your device scale should be extremely small. For example, if you use perpendicular anisotropy material, maybe you have to make probably 20 nanometer below.
Yeah, just now you show the results weight is 400 nanometer.
That's right. So it's about 400 nanometers. So obviously, it's all due to the domainal propagation and domainal based switching. Yes, you are right.
Yeah, okay. So when you're studying the 10 micrometer device and the 400 nanometer device, what did you see the difference of the domain propagation or domain motion, domain one motion?
Sure. So our speculation is, if device is so large, then you have, basically averaging effect. But if device is getting smaller and smaller, then the exchange bias is maybe not very uniform, because typically this exchange bias is the interfacial uncompensated spin phenomena, and we do not have a sort of homogeneous uncompensated spin across the whole uniform area. It's impossible. Okay, so basically you have kind of localized maybe spot of this uncompensated spin, and then this exchange bias phenomena may happen mostly around that area. So that is our speculation.
Okay, thank you. Thank you. Thank you, Prof.
Okay, let's thank you, Prof. Yang again. So it's the time for this talk. So we'll move on to the next talk.
Thank you very much. Yeah.
So the next talk is by Professor Yasuhiro Fukuma from Kyushu Institute of Technology, Japan. And the title of the talk is Classification Tasks Using a Non-Linear Magnetization Dynamics. So, Prof. Fukuma, please share your slides.
Thank you. Okay, I should start this slide. Can you see?
Yeah, we can see your slides.
Okay, thank you very much. So it's that first of all, I want to thank to the organizer for giving me an opportunity to talk here. My name is Yasuhiro Fukuma from the Kyushu Institute of Technology. My title is here, but in this talk the first that I want to talk to about that is material science of that spin-Hall effect. Then I want to move to that is the computing device part. So first of all, I want to recap that memory application. This is the typical ferromagnetic material. It shows that is this behavior. That's why we can use this kind of ferromagnetic material as a memory application, recording the digital state is 1 or 0 by switching the direction of the magnetization. So this is the schematic diagram of that MRAM, toggle MRAM application. When we apply that current into this line or word line, we can generate that magnetic field along the wire. Then we can switch the magnetization state in the free layer. For that breeding part we can use that magnetic tunnel junction. The resistance state is changed according to this is the magnetization configuration between the free layer and the fixed layer. In case of that is the parallel state, it shows that lower resistance state, and in case of the anti-parallel, it shows that higher resistance state. In the case of this kind of the writing scheme using that excited field, there is a problem with that writing is that operation margin for making that high density of that random access memory. That's why now is that writing scheme is changed to that spin transfer torque. In case of that with the spin transfer torque is that we can inject the spin current from that pin layer to that free layer. Then is that change that is that magnetization direction. But is the problem with this is that writing scheme is that when we apply that is that the current into the barrier layer for the writing scheme is that we need to apply that very high density of that current. It causes damage to that very thin is that this barrier layer. That's why endurance it could be the problem for that very fast cache memory application. That's why so now with the recently is that this is the spin orbit torque is the classic one. In the case of that spin orbit torque, when we can apply the current along that the altitude like this, then we can inject that spin current into the free layer. Then we can control the magnetization in the free layer. So how is that can we generate that is that the spin current is that from the altitude. Is that this is the three candidate is that mainly is that spin Hall effect, Rashba-Edelstein effect, and also is that spin momentum locking state in the topological the insulator. For example, is that when we use that is the tantalum as that is the altitude, then is that when we apply the current along the wire, then is that this is the free layer. Then is that we increase the current, we can do the switching. Then is that applying the opposite direction or current. Then is that we can do the switching. Is that this is the bulk effect with the spin effect. Also, in the case of this kind of the interface, here is the silver bismuth interfaces. There is the Rashba effect. Rashba effect shows that this kind of spin polarized is a band structure. Is that spin state is the depending on the momentum of the electron. For example, we can get that the electron with this momentum, we can get that spin. In the case of that is the momentum with direction, we can get that downspin. Then is that we can see that this kind of spin to charge conversion behavior at this the interface. Also, is that in the narrow gap semiconductor, is that in case of the bulk, is the gap is open, but at the surface state with that spin orbit interaction, we can get that this kind of the spin polarized surface at the only for that surfaces. For example, is that we can see that this kind of the charge to spin conversion effect as a function of that is the Fermi level. I mean that this is the case of the bismuth antimonide telluride, but is that changing the function of the antimonide, we can tune that Fermi level like this. Then, for example, at the Dirac state, is that upspin and downspin is the degenerated. That's why the conversion efficiency will decrease like this. But is that, for example, in the valence band, we can get that this kind of high value of the conversion efficiency from the charge current to spin current. But in this study, is that we mainly want to focus on the spin Hall effect because of the bulk effect. The spin Hall effect is that theoretically is that predicted is that to almost 2 decades ago. Original work is more than that 40 years ago. The important message from the prediction is that is the direction of the charge current and the spin current, and the direction of the polarization is that orthogonal to each other. And also is that we call that is the conversion efficiency between the charge current and the spin current is at the spin Hall angle. So after that is the theoretical prediction is that we can observe that the experimental is that report. That the first demonstration of the spin Hall effect is done by in that semiconductor. After that is that there is that report for the metal materials. For example, is that this is the first cases for that aluminum. Is that to observe the spin Hall effect of the aluminum, they use that this kind of lateral spin bulb structure. They inject the spin current by using this kind of ferromagnetic altitude. Then spin current is injected in the aluminum wire. Then is that there is a conversion from the spin current to charge current, then detect the voltage. Then is that what is important in this configuration is that is the direction of the charge current, spin current, and that is the polarization of the spin should be the orthogonal to each other. That's why it's when we rotate the spin polarization from the in plane to out of plane. By using the magnetic field, we can detect the signal like this. But in case of the aluminum, as you know, is that this is the lighter element. That's why weak spin orbit interaction. Only at the lower temperature, we can observe that is the spin Hall effect signal. But when we use that platinum, the platinum has a strong spin orbit interaction. That's why we can get that really is the clear signal, even though at the room temperature. So is that this is the prediction of that spin effect for the transition material and the 5D transition material. It's theoretical work. Then is that what we can see here is that compared to that is that 4D and 5D, of course, is that 5D has the stronger spin orbit interaction. That's why we can increase that spin Hall effect. And also is that here is that the sign of the spin Hall angle is changed from the negative to positive. Is that due to that is the total spin angular momentum. Is that negative side is that less than the half of the momentum, and is that here is more than half of the momentum, then change the sign. This kind of the theoretical work is that also recapped by the experimental work. Now is that we can see that is the spin Hall effect in that many different pure material. What we can see here is, for example, beta tantalum, beta tungsten shows that larger the conversion efficiency, but this beta phase is the non-equilibrium state. That's why we can see only in very thin layer. That's why for the bulk material, we can say here is that conversion efficiency is not too high. It's less than the 10%. Not only for the is that metal, also we can see that spin Hall effect in the oxide material. For example, here is the iridium oxide. Actually, in case of the iridium oxide, is compared to the platinum, that the spin Hall effect is not too high. But we can see here that the resistivity is increasing. That's why, for example, is that when we consider the spin current detection by using the electrical signal, for example, if I want to convert the spin current to voltage, this is the good for. That's why is that for comparing that is the conversion efficiency from the spin current to charge current, the iridium oxide material shows that with the similar is that how should I say is that figure of the merit compared to the beta tantalum is the beta tungsten. Because these material is that shows that higher resistivity, that's why it's good for the detection. But what we want to get here for that is it's a neuromorphic computing application using the spin orbit torque is the higher conductivity, and that the higher is the spin Hall conversion effect could be better. In this sense, is that we focus on that is the platinum based material. Then is that here is that there are several reports for increasing the spin Hall effect in the platinum by using the alloy. For example, by using that alloy with the gold or MCO, we can see that this kind of enhancement. But general trend, what we can see here, with is the decreasing the conductivity, is that spin Hall effect is enhanced. That's why is that we should to enhance that is the spin Hall effect around here. We need to control that impurity in that is the platinum layer with that good accuracy. In this sense, is that we use that ion implantation technique in the platinum layer. We can use this kind of very small is that acceleration is that equipment. Then is that we inject that is that sulfur impurity into the platinum layer. So this is that is that we deposit the platinum layer on that silicon is that wafer with that oxide layer. Then also is that we put that is that the MgO capping layer, and also is that aluminum is the oxide capping layer. Two is that decrease the damage of that ion plantation. Then is that this is the platinum layer with that ion plantation of that sulfur ion. What we can see here, this is that is the cross-sectional is the team image. We can see that no strong degradation of the crystallinity in the platinum layer because we use that is sulfur is the right element. That's why we can inject that is the impurity with that lower is the accession voltage. That's why no is the strong is that damage to that crystal properties. Also is that we did that is the energy filtered is the electron energy loss spectra of the platinum, the sulfur. What we can see here, this is the platinum layer. Then is that this is the sulfur element mapping. Then is that more sulfur is that implanted in this oxide layer, but also we can see that is that sulfur ion in the platinum layer. Then is that from this picture we can estimate that is around the 10% impurity in here. Then we remove that oxide layer. Then is that we deposit the permalloy on that sulfur implanted platinum. Then is that for the characterization of the spin Hall effect, we use that this is the spin torque ferromatic resonance measurement. In this measurement, we apply that microwave current into the platinum layer. Then is that this current generates, of course, is the electric field and also generate the spin current as well. Then is that for example, is that when we apply the microwave is the current into the sample, we can see that this kind of rectifying voltage. This is the voltage is the comprised of that is the symmetric part and antisymmetric part. So is that we can get that this kind of rectified voltage. Then is that this is the symmetric component is from that spin transfer torque. And also is that antisymmetric, there's this kind of green antisymmetric component. This is mainly from that electric field torque from this. That's why is the compared to that is that this to origin, we can estimate that is the efficiency of the charge to spin conversion efficiency. Then is that this is the result of the Stephen spectrum for the platinum layer and the sulfur implanted platinum sample. As a function of the frequency. Is that then analyzing this spectra, we can estimate that this damping factor of the platinum is also is the effective magnetization. Is the damping factor of the permalloy, the effective magnetization of the permalloy. So is that what we can see here is that in the case of that sulfur implanted platinum, we can see the increase of the damping due to the larger spin pumping effect. At the same time, we can see the decrease of the effective magnetization for that is sulfur implanted sample. Is that due to that is the increase of that is the perpendicular magnetic entropy. Also, is that this is the conversion efficiency we estimated from the ratio, the symmetric component and the asymmetric component. We can see here it's almost 3 times enhancement of the spin Hall angle from the platinum. Then it's almost the independent behavior as a function of the microwave frequency. Then also is that we check that is that the spectra as a function of the inferring angle. Then is that from here, what we can see here, both symmetric component and symmetric component show that cosine phi, sine phi behavior. Actually, we can say this behavior is that expected from the detection efficiency, also from the torque. That's why is that from this fitting, we can conclude that all the torque of circuit here is that expected from the measurement, the setup. I explained it is that in the previous slide. So also is that we can confirm that is that the spin Hall effect by using that is that this kind of is that modulation of that is that the spectra. As you know, is that we can choose that quantitation dynamics by using the spin orbit torque. That's why here in this measurement, we apply the microwave into the sample, then excite that is the ferromagnetic resonance. Then this is the ferromagnetic resonance tuned by applying that DC current. Then the spectral line width is modulated by applying that DC current. Then is that this is that case is that when we apply that positive with that magnetic field and opposite magnetic field shows that opposite behavior. That's why we can say that this kind of modulation is caused by the spin Hall effect. Then is that what we can see here, the spectral analysis, this analysis is that spin Hall angle is a little bit different, but is that we can see that clear enhancement of the spin Hall effect for that sulfur implanted platinum layer. Also is that here is that we measure that is the spin Hall effect as a function of the temperature for that sulfur implanted platinum and the platinum. This is a very interesting properties is that if the spin Hall effect is enhanced by the extrinsic mechanism, like a skew scattering or side scattering, the spin Hall angle increase with decreasing the conductivity. But it's that, you know, this is a metal. That's why conductivity is increased with conductivity is increased with decreasing the temperature. At the same time, increasing the conductivity is the spin Hall enhanced for that sulfur implanted platinum. That is the clear enhanced mechanism is that not clear so far. That's why to understand the origin, we need to study more in detail. But also is that we can record this is the figure again for that is the spin Hall effect in the platinum-based material. Actually, also is that we make the sample with that is the oxygen implantation and also nitrogen implantation. With increasing that is the implantation concentration, conductivity decrease, but is that spin Hall angle enhanced. Actually, we can see that large enhancement of the spin Hall of the sulfur implanted material. That's why is that if we can see here, we can find out material around here at room temperature, it could be the good for that. The spin orbit torque is that memory and that computing application. Then now is that I want to move to the topic of the computing part. So this is the schematic diagram of the neural network. This is this technology opened the door for that artificial intelligence as that classification task, recognition task, and also prediction task. But now is that we increasing that number of the data for inputting, then they are fighting with that very high is that it's the running cost. With that is the CMOS technology. What is important of the network here is that non-linearity. For example, is that by using that kind of CMOS technology in the hiding layer, they are changed the number of the nodes like this. Then they are trying to making that non-linearity in the network. But when we use that this kind of is about computing, we start with the non-linear physics mechanism. Here we can say it's the magnetization dynamics in the Spintronic devices. Then is that in this case is that we can largely decrease the cost of the run. In the case of the reservoir computing, is that in the network that is this is the weight of the running is fixed. We can do the justice that adjusting the weight only for the output. That's why if it's that is that we can get that is that good prediction or separation task. This kind of reservoir computing is good for that small devices with the lower power consumption. Then is that we try to use that with the magnetization dynamics for that is the computing task. Actually, this is the similar structure for that experimental work. What we do here, we did that is a mathematical simulation with that is the pulse inputting. For example, is that with that is that spin orbital. These are the simulation parameters. And also we apply that, for example, this kind of the pulse scheme. Then instead of applying that pulse, then they can inject the spin current into the formative layer. Then it's by the competition between that is the damping torque of the precession and also anti-damping torque from that spin orbit torque, it started the process like this. When we increase the current, we can see that large precession like this. Then this is the trajectory of the magnetization. In the case of that is that the small current, we can see that this kind of small precession. But when we increase the current, this kind of trajectory is strongly modified. Then is that if this kind of trajectory is drastically changed, then is the effective magnetization decrease. That's why is that we can see that is the decrease of the resonance frequency in the spectrum. So then is that by using this kind of pulse scheme, we try to do that is the 4-bit pattern declassification by using that is the pulse scheme. For example, when we apply this kind of pulse, actually the pulse is the input, then 1, here is the 0, 0, 0, for example, in the case of the green. Then we can see that is the precession only in this region. Then in the case of the 0, 1, 0, 0, mean that is that we put that the second pulse is on, then off. Then we can get that this kind of dynamics. The similar situation for third, fourth. Actually, we can see that is the similar behavior for the different one-digit input. Of course, from this is time domain data, by using the fast Fourier transform, we can get that this kind of frequency domain spectra. almost for that is the different input, almost show that similar behavior. Of course, when we put that 2 is that 1 input, we can increase that is the amplitude of the precision. But it actually is that no difference for the 1 1 0 0, 0 1 1 0 or 0 0 1 0. In the case of that, if we separate the this is the input 1 1, then we cannot see that clear difference. That's why is that this kind of scheme does not work for that is the classification task for the 4-bit pattern. That's why is that we use that this kind of fast excitation pulse, then turn on that is continuous is that the current here. Then we put that is that 1 0 0, for example. Is that this is the case of the 0 0 1 0. In this case, here is that the first excitation part is that within the 10 nanosecond. Then is that here is that somehow is that it's just that is this excitation part here. Then after that is there is that computation task. What we can see here is that we can see the clear difference between that 1 0 0 0 or 1 1 0 0. By using that fast Fourier transform, we can convert from that time domain data to that frequency domain data. We can clearly see the difference among that 4 different patterns. For example, here, in the case of that 1 1 0 0, 0 1 0 0, we can see that it's clear difference like this. To understand this behavior is that we check it that memory capacity of this spin Hall oscillator. The memory capacity is the characteristic, is the properties of the network to that linearly is the reconstruction of the past input signal using that present input. What we did here is that we input that random pulse sequence like this, then try to reproduce by using the delay 0, delay 1, delay 2, or delay 3. What we can see here in the case of the modified scheme is that with the excitation part. Regular scheme in that is the first scheme. Of course, in the case of the no delay, we can reproduce that is the input signal from the output. But in the case of the D1, regular pulse is that we can see the good fitting like this. But is that when we increase the delay, then it's getting hard to reproduce. Then is that from that is that correlation is the coefficient, we can estimate the memory capacity of this is the spin Hall oscillator. What we get here is that the modified is the pulse scheme, we can enhance the value of the memory capacity. That's why we can say that they can memorize the previous input in the case of that modified scheme. That's why this is the summary of the 4-bit classification pattern with the different pulse scheme. In the case of the regular pulse scheme, we can see here, of course, in the case of the 1 1 1 1, we can increase the large signal, but here is the very small signal. It's difficult to see the difference. But in the case of that modified pulse scheme, we can see the clear difference like this. Okay, we should stop it around here. Okay, then also is that we did that is that tested is the classification task of the modified is the NIMS handwritten digital pattern like this. In this pattern, there is the 28 by 20 pixel, but is that in the case of that spin Hall oscillator, we can just input that 4 number. That's why is that from that 28 by 28 pixel, is that we can change through that spin Hall oscillator, we is the converted to the 196 output. Then instead by using that is the pursued inverse matrix calculation from this output to the reader pattern is that by using that is that the learning is that data. Then is that we try to reproduce that is that digital number. Then is that this is the result of that is that this is the case of the regular pulse scheme, and this is the case of the modified pulse scheme. Then by using just changing that is that this kind of pulse scheme, now we can achieve that over 80% of the classification task for the MNIMS handwritten digital patterns. So is that this is a summary of my talk. Is that toward that is brain inspired computing using the spin of the talk. Now is that we can find out the new material. Also is that by using that nonlinear magnetic dynamics, by using the spin talk, spin of talk, we can do that with the computing task. So is that this is an acknowledgement of the collaborator and funding agency. And thank you very much for your kind attention.
Thank you, Professor Fukuma, for the excellent talk. The talk is now open for the discussion. Okay, Prof, may I ask a question? Hello, Prof, may I ask a question?
Yes, yes, please.
Okay. So in the implantation data that you showed, sulfur gives larger enhancement in spin Hall angle compared to oxygen and nitrogen. I was wondering why is that? Why is sulfur giving maximum increase?
That is a good question. So far is that I don't have any clear answer to it, but it's that so somehow yes, it's
Okay, actually I also have another question.
Yes.
So you said that when you reduce the temperature, the conductivity increases, right? And hence you get larger spin Hall angle. So my question is this universal that when you increase the conductivity to increase the spin Hall angle, or it just for some cases?
Oh, it's in the case of, for example, is that we can say is that there are two different mechanisms of the spin effect. It's like an anomalous Hall effect. It's intrinsic origin or extrinsic origin. Extrinsic origin is mainly scatter is done by the impurity of some scattering factor. Right. In this case, is that for the Hall effect, we need to bend that electron like this. That's why some is that scattering factor is very important. In this sense, is that when we increase the resistivity, this kind of scattering we can enhance. That's why the spin Hall effect should enhance. But in case of the sulfur implanted is the platinum, with increasing the conductivity, also this kind of is that scattering enhance. Maybe this kind of thing could be related to some intrinsic properties of the material.
Okay, thank you. So we have time for one question. Yeah, Dr. Ramu, please go ahead.
So yeah, for this particular slide, like there is like a spin Hall angle with respect to the temperature. So the maximum temperature applied is like 300 Kelvin. So did you have any study more than that, like more than 300, and did you see any change?
Sorry, we only have the raw temperature measurement system. That's why is that we cannot measure
Yeah, because actually I'm thinking like if I want to implement in this CMOS devices, because we need higher temperatures. So what would happen to the diffusion of this sulfur into the ferromagnetic materials?
Yes, that could be a good question. It's in the process, with the process, yes.
Okay, yeah, thanks.
So I think we are running out of time. So let's thank Professor Fukuma again for the excellent talk. And now we'll move on to the next talk, which will be given by Professor Rasdeep Singh Rawat from NIE NTU. And the title of the talk is Magnetoimpedance and FMR Probing of Magnetization Dynamics and Relaxation in YIG.
Thank you, Chairman, for the introduction. Can you hear me and can you see my slides?
Yes.
All right. So good morning, everyone. I'm Rajdeep, as introduced, and the title of my talk was already mentioned by Dr. Durgesh, but there is a slight modification. I'm not going to talk about the magnetoimpedance part. What I'm going to focus on basically is magnetization dynamics and relaxation in YIG thin films. And before I proceed on to my outline of the talk, let me first of all acknowledge various collaborators, which are listed over here. Just now, Professor Fukuma gave the talk. So he is our big collaborator for the last 5 years. And we actually started working on this field with his active collaboration. And also Professor Prem from SPMS, Professor Mahindran, and Professor Asada. And the team that has been working from our side over here are listed over here. 3 research fellows, Dr. Rohit, Dr. Joseph, Dr. Surbi. Dr. Joseph has left our group and has joined Professor Marshall's group. And Mayank Mishra is our research associate, and 3 PhD students, Saurabh, Shilpa, and Avinash. Let me see whether it is moving. Why the slide is not moving. Okay. Yeah. So as we know that when we have a magnetic moment, if it is placed in a magnetic field, the minimum energy or the equilibrium position is when it basically it's aligned with the magnetic field, like what is shown in the diagram on the left. Yeah, this one. But if due to any reason this magnetization is not aligned with the magnetic field, then what is going to happen? It will basically be in what we call as the excited state. And definitely when it is in the excited state, it will have the tendency to lose the energy. And that means it will try to go towards the equilibrium position once again. But it doesn't go to the equilibrium position directly like over here like that. But what happens because of the torque that it experiences, which is given by M cross H, it actually undergoes a precessional motion like what is shown over here. So this is what we normally refer as the magnetization dynamics. And if this enforcement of the tilting of the magnetization is done with an HRF, that means a radio frequency magnetic field, then it will continue to oscillate, or it will precess at the frequency of this RF field under resonance condition. And we call that as a uniform precession. But what is also happening at the same time is that this precising magnetization will also lose its energy through various different processes. And then there can be an attenuation in the magnitude of this, you can say the conical motion, and it will spiral towards the effective equilibrium field. And that is what we call as the magnetization relaxation. So there are different modes by which this magnetization relaxation can take place. For this particular case today, I'm going to discuss this magnetization dynamics and relaxation in this material system, which is called as the YIG, the YIG. It's a very important material for the reasons which I'm going to mention later on. So basically the outline of my talk is I'm going to talk about this magnetization relaxation process through 2 different mechanisms. One is called as the 2-magnon scattering, and the other one is the spin pumping. So I'm going to discuss that. But as you know, this conference is about computing. I'm also going to correlate it to how it can be used, in computing, and that brings in what is called as spin wave computing. So I was lucky so far that nobody has talked about that. But at the onset of it, let me first of all say that we have not done any work on the spin wave computing. But with our background in YIG, which we have been working for the last 3 years, particularly because of our Tier 2 project on Rashba effect, where we were working on this ferromagnetic insulator material interface with the high-Z materials. So we have confidence that in future, if we want and if we get the right collaborator, we can also venture into this field. So let's just start. So this next slide is, of course, I think I should not spend time on this because many people have already talked about it. The current computing technologies are basically CMOS based, and they so far are able to follow the Moore's law because of the many disruptive technologies that have been developed in this field. But it is expected that in a decade or so, they are going to slow down because of various reasons which are listed over here. And people are looking for either CMOS compatible alternative computing technologies or even beyond CMOS. And Spintronic is identified as one of those beyond CMOS technologies or CMOS compatible technologies, like what Professor Prem's CRP project is about. So some words about the physics of the spin wave. So as I just mentioned, that if you have a magnetization which is not aligned with a magnetic field, then it experiences a torque. And that is basically going to give us this precessional motion, which is governed by this, what we call as the Landau-Lifshitz equation. But as I also mentioned that this, because of you can say the decay of energy or the loss of energy from this excited mode goes into the spiral path, which actually was given by the Gilbert, and we have this what is called as Gilbert damping factor in the equation. So I'm not adding those terms because I'm not discussing the spin transfer torque and the other things. So you saw those two other terms in Professor Fukuma's talk just now. Now, let's try to understand then what is this spin wave. So, if we have this spins, if they are being forced by the external magnetic field, which is like a driving oscillators, then they may spin together in unison, together in unison all along. That means in that case, my magnetization basically is a function of only time. That means over the magnetic volume, there is a constant phase between them. They are in the same phase and they are all excited or oscillating together. That is basically referred as the spin wave with the spin wave vector 0. Basically, because if they are all in unison, then the wavelength of this wave is infinite. So my K value is basically 0. So that is called as the K0 magnon or K0 spin wave. Now, what happens is that there can be situations, particularly when there is a scattering that can take place in the system, then the phase may not be the same. That means there can be a phase lag between these spins, like what is shown in the diagram over here in the diagram B on the right. So as you can see, if you move across this two-dimensional array, either to the right or to the down, you can see that the phase of the spins are not the same. There is a constant phase difference between them, and that basically generates what we call as the spin wave. So a spin wave basically means that over your magnetic volumes, the spins are not precessing in phase, and then therefore there is a spatial dependence. That means the K dot R will come into the picture. And like what you see over here, the spins are not in phase, and therefore there is a wave that you can feel to propagate along this medium, and those are the spin waves. And this is spin waves. Okay, let me see, it's not moving. Okay, so these spin waves have several features which make it very useful for the spin wave computing. Of course, spin wave have lots of applications which are listed over here, but particularly for the spin wave computing, you can also use them. And there are several features that actually helps in this application for the spin wave. For example, they have wave-like nature. And since they have wave-like nature, they actually are very suitable for the majority gates. And as you all know, there are many technologies which are trying to use these majority gates, which also because of their simplification, which CMOS technology actually cannot implement. Moreover, the spin waves are typically in the gigahertz frequency range. And because of that corresponding wavelength is actually in the nanometer wavelength range. And because of that, the miniaturization of the device is very much possible. So that definitely is the case. In addition to that, if you have a low amplitude spin waves, so these low amplitude spin waves are non-interacting, and that actually allows or enables the multiplexing or parallelism, which of course is also very useful in any computing devices. Whereas at the large amplitude, this spin wave brings in the nonlinear behavior. And like what Professor Fukuma was saying, this nonlinear behavior is something people are looking for when you want to implement them for the, say, suppose the reservoir computing. And in addition to that, the propagation velocities, that means the velocities at which you can make the information move, that is the group velocity of this spin wave, can be several kilometers per second. So they can be pretty fast and then can travel over here. Now, the spin wave have other advantages. Using spin waves, you can do encoding either using the amplitude, like what is mentioned over here, or you can do it using the phase. Even in the amplitude, for example, if you don't have a spin wave, you can call it as a state 0. If you have a spin wave of finite amplitude, you can call it as a state 1. But you can also have a multi-level amplitude. For example, you can have different thresholds, say suppose threshold X, or maybe a bigger threshold Y. And if you have a wave or a spin wave with the amplitude greater than the greater threshold, then you can call it as a state 1. Or if it is between these two thresholds, it can be referred as the state 0, or you can have state -1 if it is less than the smaller of the amplitude. And similarly, the encoding schemes can be derived using the phase. If they are in phase, it's a state 0. If they are out of phase, it can be state 1. Or it can be the phase, not necessarily be in phase or out of phase. You can have intermediate phase like pi/2 also. So that gives you multiple level encoding. And you can also mix the amplitude and the phase as well, which is shown in the right diagram. And then you can have even more states possible over here. So multi-level encoding is possible using this spin waves. Now, as we all know that for CMOS technology, the basic computing element is a transistor, whereas for a spin wave, it is the spin wave guide, the conduit. And one of the requirements for this spin wave conduit material is basically that it should have low alpha, that means low damping factors, because if the wave propagates in that, it should not damp by itself, and then that will lead to the change in the amplitude. And if you have the amplitude-based encoding, then the state will change. So you don't want that. So they need to have a low alpha, as well as a high Curie temperature, as well as the higher magnetization. So, and for that purpose, YIG happens to be an excellent material. So this is a table which shows several different properties. And if you look at the last column, just look at the last column over there, you can say that the propagation distance for YIG, if it is a micrometer thick film, is of the order of 25 millimeter. While for material like permalloy, which is another hot material, if you want to go for conducting ferromagnetic for the spin wave generation, then the propagation distance is less than that. Okay, so lifetime of the spin wave survival is also longer. So by this table, actually, if you carefully study it, YG indeed is one of the good materials that one can work on. Of course, the criticism will be then you cannot have it CMOS compatible, because then because YIG is not CMOS compatible, and the growth conditions are also not very useful. But this most recent roadmap of the spin wave computing that has just come out by Andriy Chumak and several, I think more than 60 co-authors, that highlights the YIG as one of the main materials that people are focusing on. And even for YIGs, there are several schemes through which you can deposit it. For example, the liquid phase epitaxy is the most favorable one, PLD, and of course the magnetron sputtering, which people are trying to explore more, because that is what the industrially more compatible is. So some results that have been shown over here for the YIGs of the different thickness. Growing YIGs, the films of very thin with a good damping factor is still a challenge. For example, over here, the YG film with the damping factor as low as 10⁻⁻5 for 75 nanometer has been demonstrated. But of course, when you decrease the thickness, the damping increases. So that is what people are looking for. Now, with that as an introduction, let's move on to the relaxation dynamics. And I'm going to start with the two magnon scatterings. Now, just a few words about the magnetization relaxations. So the relaxation, as I mentioned, is that the excited magnetization, basically when it is precessing, loses its energy and then it moves towards the equilibrium state. So there are several mechanisms by which this magnetization can relax. And some of them, they are intrinsic. Intrinsic basically means you cannot control them. You don't have a control over there, and they will be there. And of course, in certain situations, some of them will be dominated compared to the other one. But most intrinsic one, of course, is the spin orbit relaxation. So I'm not going to go into the details of that. Let's look into the extrinsic mechanism. And the first work that I'm going to discuss is with respect to the two magnon scattering. So what is two magnon scattering? Let me try to explain that part first. So as I mentioned that when we invoke this ferromagnetic resonance condition, that means where all these spins are, oscillating in unison, and their wave vector basically is zero over there. So spin waves are basically spin wave with a k vector 0. But these spin waves, if there are some scattering centers, they scatter over there or at those scattering points. And this k0 spin wave mode then degenerates into non-uniform precision modes or non-uniform precision states with k not equal to 0. and where it loses the angular momentum, which dissipates the energy to the lattice. Okay, and that makes it to go into the relaxed state. So this kind of a scattering where this K0's mode dissipates into K not equal to 0 modes is what we call as the 2 Magnoni scattering. And this basically happens when there are defects in the system. Spin pumping I will discuss later on when the time comes. So the first work that I'm going to discuss, so these are 3 works that I've listed over here related to the YIG related work that we have published. But I will concentrate on the second one, which is basically the phase set controlled by anisotropic magnons in YIG. So this 2 Magnoni scattering, first of all, we need to know how we can, probe them. So they are probed using the fMR spectroscopy, and particularly by concentrating on the line width analysis. Okay. And the ability to control these 2 Magnoni scattering in magnonic devices, of course, will allow us to have better control over the generation and propagation of this spin wave. So that is, it is good and interesting, to study them and to know more about them. So what we have explored over here, which was not done so far, is that how the phase independent, symmetries can control these 2 Magnoni scatterings and therefore the magnon propagation in the YIG. So that is what we have investigated, and that is what I'm going to discuss first. So just some word about the films that have been grown. They are 40 nanometer YIG thin films. They are deposited using magnetron sputtering, and these results, which are basically the high resolution XRDs as well as the high resolution TM imaging, shows that we have grown a very, very good YIG thin films. So the epitaxy is excellent. And so what has been done, that the YIGs with the different orientations, with the different facets, have been deposited on the different GGG substrates. So there are 3 different films that are deposited with the 3 different orientations of 001, 011, and 111. And that is basically, we wanted to investigate that how 2 Magnoni scattering is basically affected by these facet dependencies. Now, as far as the setup of this fMR spectroscopy is concerned, this is shown on the figure in the A, where when you make the RF current flow into this CPW, it generates the in-plane HRF field, and that actually makes the magnetization to precess. And then you capture what we call as using the VNA, we have captured this S11, which basically is the reflection coefficient. And those spectra are shown in this diagram. Now, these spectra, they can be fitted with the formula that is listed over here, and which have this L and D, which are basically the Lorentzian and dispersive wave factors. And from there, you can actually calculate, or you can find out what is the resonance magnetic field, as well as what is the line width DH. So those have been deducted. But first of all, what we did, we wanted to have this 2 Magnoni scattering not coming because of the use of very high power. So first of all, what we did, that we want to see that what is the region where this can be nonlinear by itself just because of the power. So we did not want to work on that region. So first of all, the power was changed, the input power was changed, because even the high input power can cause the line with radiation as well as the magnon excitation. So for that, the power was changed from -5 dBm to all the way to about 18 dBm. And at these various powers, you measure the resonance field as well as the DH values. So as you can see at the lower powers, they were really more or less constant and linear, but after that, they start to go into the nonlinear design. They start to change over there. So we did not want to work in this particular region. We wanted to work somewhere over here. And the reason basically is very simple, is that when you apply higher RF power, basically you are going to apply higher field, and that is going to make your magnetization vector to precess into a larger, you can say, cone radius over there. And as if you remember Professor Fukuma's slides just now before, if the precision cone angle is small, they are quite linear and uniform, but when it is large, they do not remain linear as well, linear all the way. They sometimes will have some kinks over here and there that brings in the nonlinearity. So we wanted to exclude that nonlinearity, and therefore rest of the experiments were done at 0 dBm. So the later on results, what I'm showing are basically at the 0 dBm. And in order to explore the effect of the anisotropy, the crystal anisotropy, the crystal symmetry on these, what we have done the phi scan. That means your applied external magnetic field was rotated in plane in 360 degree. And the corresponding results are shown over here before I go to the angular dependence measurements. But first of all, the frequency was changed And at all these different frequencies, we got these spectrums, and from there, you get these plots which are shown in results A and B. And using this Kettle equation fit, you can actually calculate what is the effective magnetic field for these 3 different orientations. And we found them to be the values which are listed over here, which actually is less than the saturation magnetization of YIG, which is typically around 175 millitesla. So you can see there is a significant difference, particularly for 001 orientation and 111. I mean, all of them, they have quite some difference. So that basically means that there is a presence of anisotropic field in these crystals, and that is causing the difference in that. So after that, as I mentioned, that we actually focused on the angle-dependent HMR. Another thing to notice over here, which is basically for the DH measurements, this one, that after the 10 gigahertz range, the data is non-linear. I mean, you cannot fit it using that linear fit. And this reason basically, this observation basically tells you that we do have this, what we call as a 2 Magnon scattering. So that is well cited in the literature, that when you see that non-linearity in your DH versus frequency curve, that basically is a clear hint of 2 Magnon scattering being present in the system. Then after that, as we did this angular measurements of the resonance field, then what you see for the different crystal orientations. So the one on the left is for 011, the one in the middle is 011, and the one in the right is the 111. And you can see that the variation is of the different type. For example, the one on the left, that means 001, it can be seen to have the 4-fold symmetry, which will fit also like to the cubical, you can say the symmetry that is observed in the anisotropy energy that you measure. So that shows the 4-fold cubic symmetry over there, whereas the 011 shows sort of a major predominantly cubic, uniaxial anisotropy. There is some trend of some cubical anisotropy component is also there, and that's why the expression is slightly more complicated. Whereas for 111, you don't see a sort of any kind of an anisotropy over here, neither uniaxial or cubic. So it is independent of that angle theta, like what you see over here. So that is the trend that we observe. So remember this, when we have a cubical anisotropy, then you get this 1 minus cos 4 factor, which actually fits that. So if this, if we try to understand what is the reason for that, actually it can be obtained from the TM images that we saw, and also if you try to see that what are the positions of these octahedral and tetrahedral sites where our ferromagnetic ion Fe3 is sitting over there, then if you have the plots of this along the different directions, then you can see for the octahedral and tetrahedral sites, they seem to form a nice cubic symmetry over there for the 001 orientation. And that is what is also reflected very well in the TEM images. You can see that cubic arrangement over there. Whereas for 011, they show uniaxial, arrangement like what you see over here, not only in the modeling, but also in the TM images. Whereas for 111, you don't see any of that. So these things, they basically correlate directly with the anisotropies that we also see in the corresponding HR plots. So you see over here, once again, it's the same, but not in the 3-dimensional, it's not shown in that contour plots, but rather plotted as a function of an angle for the resonance field as well as the DH. So you can also see, once again, it shows the 4-fold symmetry, the cubic anisotropy. This one predominantly shows the uniaxial 2-fold symmetry, but with the some kink of 4-fold symmetry shown over there. And this one, hardly any variation. So we say almost like constant over there. And these can be fitted with the different equations, which you can find from the literature, where you have this anisotropic field for the 4-fold symmetry or uniaxial symmetries. And by fitting these equations, you can actually calculate this, what is the value of H4 and H2 over there, which are listed in these tables over here. And if you look at these tables, you will find that the H4 values for the 001 is the strongest, basically, again, showing that it is having a strong cubic symmetry. or cubic anisotropy, whereas for the 0, 1, 1, it is predominantly uniaxial, H2 basically, because that value is the highest, and it is very low for the last 0, 1, 1, basically, almost like no, you can say, anisotropy over here. And similarly for the curve for the DH, that can be fitted over using this equation where we have these three constant A and C, which are related to the cubic anisotropy, and the constant B is with respect to the uniaxial anisotropy. And if you analyze this table, it actually confirms what actually is shown by the other results. So in a way, what we can say is that what we find that there is a resemblance in the periodicity of the line width and the resonant fields, which indicate the magnetocrystalline anisotropy, which basically appears from the crystalline nature of these epitaxial thin films. They play a very major role in controlling the two magnon scattering, or basically the line width, resonant line width values in this case. So these results clearly demonstrate the phase dependence and isotropic line width variation in YG thin films. So let me see how much time. Okay, I think I still have 10 minutes. So let's move on to the last part of this topic, where what I'm going to discuss is spin pumping as a relaxation mechanism. Now, before we go on to that, let me just first of all try to explain what the spin pumping is. So spin pumping happens when you have, so the results that I was presenting just now for two magnon scattering, we have just a thin film. But now we not only have the YG thin film, which is by ferromagnetic layer, but there is an adjacent non-magnetic metallic layer, which in our case is going to be PT. So whenever you have a ferromagnetic layer together with an adjacent PT layer, and if you subject this ferromagnetic layer to external oscillating RF field, that means HRF, then the magnetization will start to precess in this ferromagnetic layer, and this precessing magnetization in the ferromagnetic layer pumps the spin to the adjacent non-magnetic layer. So that is what is called as the spin pumping. So that pumping takes place only if there is an adjacent layer over there. So interface, at this interface, basically, there's a loss of angular momentum from this ferromagnetic layer, and that leads to the dissipation in the energy of the magnetization in the ferromagnet, and that leads to the relaxation. So that is what is called as the relaxation due to the spin pumping. Of course, there are several factors which affects this spin pumping. So this is the arrangement of our experiment, where you see there is a YG thin film, the same 40 nanometer thin film, coated with the 5 nanometer thick platinum layer. And then you pump, you have this signal line over here in which you have an oscillating current, which produces this time varying HRF, which is basically in this case is perpendicular to the system. So this is along the Z axis. And therefore it will make the spin to precess in the ferromagnetic layer. And because of that, there is a current J as the spin pump. It's a pure spin current that is pumped to the neighboring non-magnetic PT layer. And when we have this spin current being pumped to the non-magnetic layer, then it will produce a charge current because of the inverse spin Hall effect. So there is a charge current that will now flow into this nanomagnetic layer. And because of that, there is a voltage that will develop across it. And this is the voltage which we call as VISHE. And this VISHE voltage is given by the expression which is listed over here. But basically, it is directly proportional to the spin current that is being pumped over here. So the rest of the factors, they are constant. And there is this spin Hall angle theta SH, which is also over there. But for the PT layer, we will assume it to be constant. So what you see on the right are the spectra that we observed for this YG PT layers, but for the different orientation of YG 100, the one which has the cubic anisotropy, and YG 111, which did not have the cubic anisotropy. So that is what we wanted to see how it is going to affect. So this is through this spectrum, by their analysis in a typical conventional way, we can derive the parameters for our films, which are listed over here. You can derive your anisotropic field values. You can find out what is your M effective and so on and so forth, which are listed over here. Again, through the Kettle equation fit. Now, what we did again is that we again have a phi scan. That means the external magnetic field is rotated in the XY plane. And we observed once again the VISH wide, how it is varying as a function of this change in angle phi. Now, what is given in the literature, which is basically listed over here, and not only this, but many other things, is that the variation that is expected when you have an out of plane excitation, because I mentioned in our case, the HRF is perpendicular to this. So we are actually dealing with this case. The variation in the ISHE is expected to be fitted by this sine curve. Okay, and that basically comes because of the measurement geometry. Okay, nothing else. So in this case, the so-called the magnetocrystalline anisotropy effects were not basically investigated. So for any materials, this is basically modeling based results, and that is what is predicted. But our hypothesis is that now in our case, because we are investigating YIG with the different orientations being grown on that different epitaxy of the film, and they have different anisotropy present over there. It's a cubic anisotropy for 0, 0, 1. It's uniaxial for 0, 1, 1, and almost like no anisotropy for 1, 1, 1. So that should affect even in the spin pumping process. That means this should be modulated. So that was the hypothesis. And that is what you can see over here. If you look at the results, the cubic anisotropy, which is exhibited by YIG 0, 1, 0, 0, 1, it actually shows the modulation of your sinusoidal curve. Whereas for the YIG 1, 1, 1, which does not have any strong anisotropy, which is also reflected once again in the HR and delta H measurement, then you see almost like a perfect sinusoid fig. So, so that is what the modeling was saying, and we saw that. But as we hypothesized that anisotropy of the crystal system should also affect this YSHE voltage, and therefore VISHE should be modulated, and that is what is reflected over here. Now, what we wanted to investigate is what is the dominant factor in modulating this this VISHE. And if you just do a mathematical fit of this VISHE voltage, we can show that. So red curve is the one which is basically fitting the VISHE data with the red curve, and this is nothing but the sum of the two curves, which is green and the blue curve. And the green curve is the same theoretical model curve where we have a sinusoidal function which is fitting it. But then you can see that additional function that we needed to get that red curve is the one which is again having the same 1 minus cos 4 5 dependence, which is, remember, is coming from the cubic anisotropy. And this sine phi again is the machine dependent part, which is also need to be multiplied by that. So that basically shows that the cubic anisotropy exhibited by 0, 0, 1 crystal actually is the key factor. But then we also wanted to see that what is it in this, which part of the, which properties of the material are affected by this cubic anisotropy of 0, 1, 1. Because if you look at this VISHE voltage, which I mentioned, that is strongly controlled, is basically controlled by the spin current Js. And if you look at the expression for the spin current Js, it depends majorly on the two factors, the spin mixing conductance and the precision cone angle. So spin mixing conductance is a property which comes into a picture when you have an interface. In our case, the interface is between the ferromagnet and the non-magnetic layer. So it's basically something which controls the spin transport property across the interface. So it's a very important parameter and need to be quantified and need to be understood. And the second is the precision cone angle. So if you look at the spin mixing conductance expression, it is basically the difference of the line width measurement for the YIG PT sample as opposed to the YIG line width of the pure YIG sample. And we have these two values which are shown over here and here. If you take the difference of these two, this is the mixing conductance that is going to mimic. So what we found that the mixing conductance does have some variation. It seems to have some variation, but it is not very prominent. So we are not saying that it is totally gone or totally ignored, but this is not so prominent because the average of it is almost like a straight line. Now, the other factor that we need to explore is that what about the theta c, the precision cone angle? Now, the precision cone angle can be deduced by this expression, where it is going to depend on the HRF field that is applied and this the line width. We already have shown the line width value, so we needed to find out the HRF. One way to find out HRF is just use the simple equation, B is equal to mu naught I divided by 2 pi r. So how much current you are sending in the waveguide, you can just use to calculate, but that will be a very approximate ideal value. We found it experimentally using by finding out the power that is being absorbed by by our films. And because the power absorption has this HRF dependence, so if we experimentally measured the power that is absorbed in our system. So this is power that is absorbed in the system, power absorption for the YG 100. And from there, we actually calculated how HRF is varying. So from this, and you can see the power absorption for 1000001 is different from that for the 111. 111 still shows the, you can say, two-fold symmetry, but this does not show two-fold symmetry. This itself is quite complicated. Actually, it was mimicking something like the variation in the YISHE. So this, if you a little bit, fine tune it, or basically you can say try to remove too much of noise over there. This is what like the red curve is trying to show. And this again can be fitted with the two functions, one with the CPW contribution, which is again the sinusoidal function, the black curve, and then the effect of the cubic anisotropy, which again is the fold-fold anisotropy, which is seen over here. And if you use then this cubic anisotropy contribution and divided by the curve of the delta HM, which was in the previous slide, you can find out that your this precision cone angle shows a very strong cubic anisotropy dependence on that. So that basically explains what is happening in our system. So let me now conclude our talk. So this paper is still it's being prepared and it will be submitted soon. So to conclude, basically what we have demonstrated and explained is that the origin of this facet dependent magnon-magnon interaction in our case in YAG, and that will become very handy for those people who are actually trying to use this YAG as a spin wave conduit, because if they grow with the material with the different orientations, the different amount of spin waves can be generated over there, so they can be controlled in a way in that sense. Whereas the second part is not related to the spin wave, the one where we were doing the spin wave, spin pumping, but that will also be useful in understanding that particularly if you are dealing with the systems having cubic anisotropy, at what orientation you can maximize your spin current generation. So that will also be very useful to understand that. I think with that I stop. It's about 35 minutes. Thank you very much for your attention.
Thank you, Prof, for very insightful talk. The talk is now open for the discussion. So please raise your hand. Okay, so Prof, actually, it's not a question that I want to ask. Actually, when you were explaining that through amplitude threshold of the spin waves, multi-level states can be obtained. So I missed some discussion. So could you please help me to explain?
Okay. Yeah. So those are, first of all, let me mention that this, if you want to read more details, you can find in this paper. So I've taken the image from that paper, but I modified it to explain it in rather maybe a simpler way.
Yeah.
So what I was saying that, if you have a spin wave, so a spin wave you can just consider like this, right?
Right.
And then simple coding is that, okay, if you have a spin wave, okay, then it is a state 1. If you don't have it, it's state 0, correct? That is easy to understand.
Yeah.
Okay. Sometimes you say that, okay, no, I want to have some reference, like for example, what in TTL logic and other logics are, there are always some voltage. If it is beyond certain value, we say state 1, less than that value, we say state 0. So same thing can be done for the spin wave. If reference amplitude of the spin wave, it is less than that, you can call it as state 0. If it is greater than that, it is state 1. But then what is spin wave allows you to have different threshold levels. Different threshold level means, say suppose we define two different thresholds. One is called as threshold X, the other one is called Y, where your Y is greater than X. Now, if I have, this is therefore in this case, basically I have two reference level. And if you have a wave that is a spin wave generated in your system, which, because the spin wave computing technology is going to base on the interference of these waves. So the wave amplitude will increase or decrease when they interfere, right? Because that's how you are making them propagate. If your amplitude goes bigger than the bigger threshold, you can call it. So it is up to you how you define. I mean, there is no fixed logic over there. So that one can be defined as one of the states, says 1. And if it is between the X and Y, so if it is between Y and X, the amplitude, you can define it as another state, either 0 or -1. And the third state, which is also possible, is less than the smaller amplitude, then it can be the third state. So what you are able to have is a multiple level encoding, which is not possible in the transistor, because transistor you either use on or off.
Yeah.
So you have only two binary states over there. So you don't get multiple level encoding. And that multiple level encoding is not only in amplitude, it is also in the phase. So phase can be 0, pi by 2, or pi. Or it can be mixture of this. This one I did not explain over here, but the first part is the amplitude, the second part is the phase. So if with reference to the reference signal, if they are in phase as well as of the same amplitude, state one of the state 0. If they are in the same amplitude but out of phase, state 1. Double the amplitude, but the phase, no, the same phase, state 2. And double the amplitude phase difference out of pi, then it is the state 3, and even other possible states. So this multiple level, states are possible for this, which is also desirable in some kind of computing techniques people are trying to develop.
Thank you.
Welcome.
So I think we are running out of time. So let's thank Professor Rajdeep again for the very nice, insightful talk, and also other professors who gave presentation in this session. So with that, I would want to hand over the stage to Professor Prem. Thank you.
Thank you, Durgesh, for chairing the session, and thanks to all the speakers and the audience who attended this session. So we have one more session in the afternoon. Then to conclude, we also have the award ceremony for the students and the speakers who gave the contributed talks. So please join in the afternoon. So we'll resume the session at 3 p.m. Singapore time, 4 hours from now. So I'll pass the mic to Professor Tanaka.
Yes, we have the last session in this afternoon. So we will see you soon. All right. Thank you.
Okay, see you all. Bye-bye. Good afternoon.
Hi, good afternoon. So our certificates are really good.
Okay, thank you. Separate the one mid.
Hello.
Hello.
鈴木先生、よろしくお願いします。
こんにちは。
こんにちは。よろしくお願いします。
よろしくお願いします。 鈴木先生、the last speaker。大鳥をよろしくお願いいたします。
はい。大変な役ありがとうございました。
で、鈴木先生の発表の後に学生たちのアワードセレモニーを行いますので、
はい、了解です。
たくさん聴講されるのかなと思います。
はい。
Hello. Good evening.
Hi.
Hello, good afternoon, Christos.
May I check my computer?
Yeah,
if it's
please.
possible to share screen correctly or not.
Yeah, let me stop sharing. Okay, yeah, please.
Yeah.
Yeah, we can see the slides.
Is it okay? Can you
Yeah,
see?
okay, yeah.
Thank you.
Looks okay.
Could I try mine as well?
Yeah, please.
Sure, please.
Thank you. Share screen.
Okay.
It's working?
Yes, good. Yes.
Good. Thank you.